All right, so number 15, we have what is called a floor function. F of x equals, and do you guys see this notation right here? Looks like bars, and there's just a little piece on the bottom right there on each side. That's a floor function. What that means is any number that we plug in for x, so we're going to plug in a 6.25 in for the x, so 6.25. What we do is, this is a rounding function. We're either going to round up or round down. If it's a floor function, we're going to round down to the nearest integer, which is a positive 6. If that was a ceiling function, it would look like this. And then we would round up to the nearest integer, which would be 7. But the floor function rounds down, so we're looking for a 6 on this one. All right, number 16, we're going to graph. Notice the bars, absolute value of x. We've got that 4 out front, and we're going to identify the domain and range. So I did go into some detail on domain and range on an earlier problem. So go back to the first time you're asked for domain and range with these absolute values if you want to get just a more thorough explanation of that. Offhand, I don't remember what number it was, but probably on the previous page. So absolute value graphs, let's remember those are our V-shaped graphs. The number in front, our A value, tells us a couple things about our graph. If this number is positive, that means our V is going to open up. So maybe we'll make a little note. We know this is going to open up. And then if this number is bigger than 1, our V is going to get more narrow. The sides get closer together. If this number is between 0 and 1, more of a fractional value, our V is going to get wider. If you notice, it's just the absolute value of x there, no translations. We don't have any addition or subtraction in with the x or any addition or subtraction on the end. So that means that this absolute value function has a vertex at the origin. So we're going to start by plotting a point at the origin. Now we're going to use that 4 as our slope. We're going to go up 4 to the right 1, plot a point, up 4 to the right 1, we can plot one more. That's going to be the right side of our V. Now we want to mirror this on the other side. Go back to your vertex. We're going to go up 4, but to the left 1, and up 4 to the left 1. And you can see we have two sides of our V, and this is our absolute value function. All right, so domain and range. Again, I went into detail on a previous problem. What we discussed there was a domain for our absolute value functions is going to be all real numbers. And then the range, that's our output of our function. So two ways to think about it. Any number that we plug in for x, this absolute value will make it positive. And then we multiply it by a positive 4. So our function is going to stay positive. What we can see in our graph over here is we're starting at the vertex, and our entire function is up here with our positive y values. We don't have any function down here in the negatives. So we're going to say that all of our y values are greater than or equal to 0 for our range. All right, number 17, this is when we started to get into our exponent notation, radical notation. This is a radical notation. We can see that this little guy right here, that 8, that is the root that we are taking. So this is an 8th root. This 9 right here is a power that we are raising, and we have 3, that's our base. So when we put this into exponent notation, it does say to rewrite it using rational exponents. Remember, rational just means a ratio, which is a fraction. So we're going to have an exponent that is a fraction. When we rewrite this, we want to remember that our rational exponents are always written in the form, we always put the power over the root. That's how we put our fraction together. So we keep our base of 3, and we're going to put the power over the root. So we said that the power was 9, and the root is 8. So there is our radical expression written using rational exponents. So this 3 to the 9/8 power is the same thing as the 8th root of 3 to the 9th. These are equivalent statements. All right, so number 18, we're going to solve for x. One thing we notice right away is we have all of these 2's. Oh, base of 2, base of 2, base of 2. So we're going to use our exponent properties to simplify this. Let's start on the left side over here. When we are multiplying the same base of 2, we are going to keep our base of 2 and add our exponents. So I'm going to just write out the addition. X over 3 plus, oh, and I did that wrong, x over 2 plus x over 3. That is equal to our 2 to the 5th power. So we simplified the left side of our equation. We got that down to a single base of 2. Now what we notice is that 2 to a power is equal to 2 to a power. So when you have the same base, that means that your exponents will be the same. So that means that x over 2 plus x over 3 has to equal equal that 5. So that's the equation that we're going to write. X over 2 plus x over 3 is equal to 5. And we'll go ahead and solve this equation. So when we solve this, you guys might notice there are some fractions. My first thing I like to do is to get rid of the fractions. I'm going to multiply everything by a common denominator. So 2 and 3, a common denominator for 2 and 3 is 6. If I multiply everything by a 6, I will end up with an equation with no fractions, and it's just a lot easier to solve. So I like this to be my first step when solving an equation with fractions. So 6 times x is 6x. Remember, we multiplied to the numerator, but divide by the denominator. So 6x divided by 2 is 3x. I'm going to carry the plus. Now we're going to multiply to this term. 6 times x is 6x. We have to divide by the 3, and we get 2x. Carry your equal sign. We do have to multiply every single term by the 6, so that includes the 5. 6 times 5 is 30. Now we have a much simpler equation to solve. We're going to go ahead and add our x's together. 3x plus 2x is 5x equals 30. We can divide both sides by 5, and we get x is equal to 6. All right, number 19, we're going to solve for x. These exponents are a little bit small to see. So we have our base of 25. This is raised to the x minus 3 power raised to the second power equals 25 to the 2x plus 1 power. So just real quick, something to notice is we have the same base, but we want to clean this up a little bit. We have the power of x minus 3 raised to a power of 2. So when you have a power to a power, we have an exponent property that tells us to multiply the exponents. So we're going to keep our base of 25, but let's multiply the exponents. That's an x minus 3 times 2. Here, if I were to write it a little bit bigger, kind of looks like that. This 2 is going to multiply to that entire exponent. So 2 times x is 2x, and 2 times a negative 3 is negative 6. I'm just going to carry down the other, or the right side of our equation. 25 raised to the 2x plus 1 power. All right, so we have an equation. Our bases are the same. 25 is equal to 25. So that means that our exponents will be the same also. And that's the equation we're going to write. 2x minus 6 is equal to 2x plus 1. All right, so first thing we want to take care of is we have x's on both sides of our equation. To get those x's to the same side, we can subtract a 2x, subtract a 2x. 2x minus 2x is 0. This over here, 2x minus 2x is 0. So this takes us back a while. Anytime that you're solving an equation and your variable cancels away on you like this, we don't have any x's to solve for. We just carry down our equation. We have a negative 6 is equal to a positive 1. And we ask ourselves, is this true? Is negative 6 equal to 1? Because that's not true, that means that there is no solution to this equation. There's not a single value of x that we could plug in to make the left side equal to the right side. All right, so number 20, identify the asymptote for each function. So just as a reminder, these are our exponential functions. If you notice, we have our variable as the exponent. So what these functions look like when they're graphed, let me just show you a quick reminder. Our exponential functions are those graphs that had a curve. So for example, an exponential growth function looks something like that. If it was a decay function, it looked something like this, where it was going down from left to right. Exponential functions have an asymptote. The asymptote is where our function kind of looks like it levels off into a horizontal line. If you have no vertical shifting of your function, that vertical line is y equals 0 right here. Here's y equals 0, that's the asymptote. Our curve right here, the function, will get closer and closer and closer to that 0, but it will never actually touch it. I mean, it gets so close that to the naked eye, we can't even tell a difference. It looks like it's touching it, but mathematically, it could be like 0.0000005 units away. We can't tell that. That looks like it's touching it for us, but it mathematically will never touch this horizontal line. This exponential function, if you notice, kind of levels out into a horizontal right here. Again, this asymptote would be at y equals 0. The default is y equals 0. The only time that changes is if our function shifts up and down at all. So that might be the best way to identify the asymptote, is to figure out if you have any vertical shifting. As a reminder, vertical shifting shows up in a function where we add or subtract a value to the end of the function. So here's our function 60 to the x power. It would be on the end. It would not be up in the exponent with the x. Any addition or subtraction with the x is going to shift your x's. X's are horizontal. That would be a horizontal shift. So if we compare A and C, do you guys see how C has this -4 off on the end? That's a vertical shift. That's what it looks like. So part A, f of x equals 6 to the x, there's no horizontal shift. That means that it will have our default asymptote of y equals 0. All right, if we take a look at part B, g of x equals 3 to the x power, is there any horizontal shifting? We can see that there is not, so it gets the default asymptote of y equals 0. That's these graphs that I kind of sketched in here, something like that. So when you do have the vertical shifting, so part C, we have h of x equals 2 to the x with this -4 on the end. This -4 on the end is going to take your function and it's going to move everything down 4 units, including your asymptote. So your asymptote shifts down the same amount as the entire graph. And if we're shifting down 4 units, well, now our asymptote would be at y equals -4. Part D, we have k of x equals 4 to the x power. Plus 2 on the end is a vertical shift. If our whole graph is moving up 2 units, our asymptote is moving up 2 units as well. So now it's going to be at y equals a +2.